Okay, so number 6 asks for the typical formula for several things. Some of these are diatomic gases. Any gas except for a noble gas. Let's back it up and say any elemental gas. So any of the elements that are gases will be diatomic except for the noble gases. So this column it makes up the noble gases. Any other elemental gas is going to be diatomic, and the elemental gases are hydrogen, nitrogen, oxygen, fluorine, and chlorine. Okay. Now bromine is usually a liquid at room temperature and pressure. It happens to be diatomic too, but that's the main thing. I want you to know the gases are diatomic. Iodine is diatomic in a gas form and not diatomic in a solid form. And iodine is one of those strange elements that's either a solid or a gas under atmospheric pressures, but it's never a liquid. And it changes right about room temperature. So if you put a little solid chip of iodine in a container, you'll see purple gas in there. And then you'll see a solid chip in there at the bottom too, because you can have both states at the same temperature, usually. All right, so anyway, that means that then oxygen is going to be O2 in number 6. Fluorine is going to be F2. Hydrogen is going to be H2. But then iron, well, that's a metal, and that's just going to be Fe.
Does that have anything?
No. All the metals, if they're solids, well, in fact, all the metals, period, if they're elemental, that is, they're not bonded with anything else, they're by themselves. And except for those diatomic gases, there are very few well, in fact, I haven't asked you to know the structural forms, what they're called allotropes, of other solid forms. Okay, so except for those gases being diatomic I mentioned, you just list them like they are. Now argon is a gas. Remember, it's a noble gas, so it's just Ar. Okay. A what? A 1 next to it? Oh yeah. I mean, if I want to know if I want you to list the physical state, yes. Okay. I'm just asking you to list the normal formula for it at this point. But I mean, you could put that next to it: gas, 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 solid gas. If you want, I mean, that wouldn't harm your grade at all. Next question was what? 10. Okay. So where do we get the molar ratio from? And now it says be very specific. So the simple, unspecific answer is molar ratios come from our balanced chemical equation. The more specific answer is they come from the coefficients in front of the species in the ratio, and that comes from the balanced chemical equation. Does that make sense? You have to use the coefficients in the balanced equation?
Like the 2 in the balanced equation.
Yeah. Yeah. Right. The big 2 in front of the species name, or species symbol, and then moles of that species, and that's where it comes from, the balanced equation. So yeah. Yeah. Does that make sense to everybody? All right. Well, I'm not even writing down the answer then. Let's just say here, just shorthand it, coefficients in balanced equation. It's a bit more than that, but I'm just writing down the highlights here, okay? All right, and the next question? Do we want to go to 17 now? No. Okay. All right, let's take it one at a time. Number 2, we're saying at 3 things that a mole of a chemical is equal to. So 1 mole of some chemical we're going to call X, okay? And we're going to have that equal to 3 different things, all right? And the first thing is a mole of X is equal to 6.02 times 10 to the 23rd particles of X. All right? And then it's also equal to the sum of the atomic masses of all the atoms in a formula in units of grams. Okay? And that's the one we've been using. We've been using this one like crazy, this whole unit, right? The last one is, it's also equal to 22.4 liters of X when X is a gas, but only under special conditions. The conditions are the temperature is 0 degrees C, and the atmospheric pressure, or the pressure under which the gas is being held, is 1 atmosphere. So those are the three things that a mole is equal to. And if you went through the unit, there's something we haven't really discussed in this unit yet, and that's the mole map. It's in the unit packet. Okay. Now, it's really kind of just a guideline for doing stoichiometry. Yeah, let me show you the mole map, because I like the mole map. You know. All right, the mole map. Now, there are different versions of the mole map, but the mole map is how you do stoichiometry. All right, and the key thing is this, where you are going from one species to another. That's the mole to mole conversion using a molar ratio. Okay, but we can go from number of atoms or molecules or formula units of a substance to any one of these other things down here: mass, volume of a gas, concentration of a solution. We can start with the mass. This is what we've been doing in this class a lot, starting with the mass of one substance, getting it in moles, going from moles of substance A to substance B in moles, and then finally going to, where's the mass of substance? Well, it should say B down here. I don't know why I have A's down here. All these should be B's. You change that one. Okay. Down at the bottom, that should all be B's. Okay. Gas volume, there's that 22.4 liters we just talked about. Okay, we use that to make a molar, it's called a molar volume ratio. Concentration of a solution, you can go through the same thing to get the concentration of another solution, or the mass of a substance. All those things can be done. What? Page 274, right. So I'd hang on to that. That's a really neat reference to keep in mind, because all stoichiometry can be done from this mole map right here. Okay, you just have to. The only complex thing, and I don't know if it's all that complex because we've done it a lot, is that converting, building our molar mass ratio and using that. Okay. So let's see. Now you want to do which one? 7? 14, I'm sorry. Where did we get the molar ratio from? Didn't we just answer that? Oh, 14? I'm looking at the CP reference. I'm sorry. It's that practice test. Sorry, looking at the wrong practice test. 14, what is a limiting reactant, and how do we determine which reactant is the limiting reactant? In this class, in number 14. Oh, you got it already? Well, since you asked, and since I'm recording it, and since somebody might be watching this, let's go ahead and say what it is, okay? Yeah, I didn't get that either. The way you get, and besides we got a new student in here, and I don't really know how much she knows, so let's go ahead and make sure we say it. All right, so the way we do it is we do a mass-to-mass calculation twice. Once from one reactant and second from the other reactant, always going to the same product, the product we're interested in. The least amount of that product we reach tells us what what the theoretical yield is. And whichever of the two reactants we started with to get that theoretical yield, that reactant is the limiting reactant. Okay? limiting reactants by definition are the chemical substance that runs out first in a reaction. And then if it runs out, the reaction has to stop. Okay? So a definition, a pretty simple definition of a limiting reactant is it's the reactant, the chemical species that runs out first in a chemical reaction. By extension, then it means the reaction stops when it runs out. So you can't produce any more product once the limiting reactant runs out, unless you add more. Does that make sense? Okay. Next question. Which one? 12. Okay, 12. Question 12 on the practice test. What is the maximum amount of product that can be reduced from a given amount of limiting reactant? I kind of just said that. Theoretical yield, yeah. That's it. Okay, yep.
Number 8.
Okay. What is formula mass? Formula mass is the molar mass of a formula, something that has a formula. Molar mass. No, molar mass is, right? Right. Well, formula mass is just it's the same thing, but just for any formula you're working with. H2O's formula mass is the same as its molar mass. Well, it's a little, yeah, but see, there's also an atomic mass and therefore a molar mass for electrons or protons, which is not, you wouldn't have a formula mass for that, but you would have a molar mass for that. Okay? What you can see, you can divide them out. All right? But almost all the time that we get molar mass, we're getting a formula mass. Okay? Almost every time we do it. But there are cases where you get a molar mass that doesn't actually involve a formula mass. Okay? But so it's kind of like there are different types of different classifications of formulas. Okay? The different classifications that fall under this big classification of molar mass. Are you stretching or you got a question? Okay? Number 13. What do we in this class use an equality statement to construct? All conversion units. And in order to emphasize where conversion units come from, we always write, you're required to write an equality statement when you build a conversion unit every time. That's why when we reach the end of the molar mass calculation, we always say this mass of the species equals 1 mole of the species. That equality statement then is used to build the conversion unit. Okay? So instead of just taking a shortcut and saying, build it this way, I want you to know why we do it that way. And we're emphasizing that by writing equality statements every time. Okay? Next question.
What exactly is an equality statement?
An equality statement is any factual statement in which we say that an amount of some measurement of a chemical species equals an amount of some measurement unit of a species. Okay, that's what an equality statement is. Yep.
What is molecular mass?
Molecular mass is the other common subcategory of molar mass. It just means the molar mass of a molecule. Okay. Remember when we were talking about ionic compounds typically don't form molecules. They form these large structures. Okay. And so for ionic compounds, typically we talk about their formula unit. But when we're talking about molecules, we're talking about their molecular unit. Okay. So that's just, we've got molar mass is everything, and under molar mass you got formula unit and molecular mass. Formula mass and molecular mass. Okay? Just depends on the species. Most of what we're dealing with in this unit are the detail stuff, the mass stuff we've been doing have all been ionic compounds. So we're working with formula masses in this unit. But in previous units we've done a lot of things in molecules. And so they're molecular formulas. Next question. Yes?
When you're calculating the percent yield,
Mm-hmm.
what exactly are you getting? I know it's theoretical, it's actual yield over theoretically times 100, but what exactly are you getting? What is it for?
It's a kind of comparison for how efficient your collection process is. Okay. Theoretical yield is the absolute maximum of a product that you can get. Okay. You can't get there. It's like absolute zero. You can't get there. Okay. But it is theoretically how much, if everything were perfect, you could get, and nothing is perfect. Okay. So we compare how much we actually got to that theoretical maximum by using what's called a percent yield. Okay. Right, there's no such thing as pure water. You can buy something called ultra pure water, but it still has some dissolved gases and things in it. You just can't get perfectly pure water. It's just not possible. Even then, you got autoionization taking place. Okay. Well, anything else? You're still not going to get out. Filtering water won't get out dissolved gases. You can get, I forget what it is. It's like 99.98% ultra pure. Is ultra pure or something? So that's at 0.02%. There's still dissolved gases in there, and that doesn't even take into account the autoionization we're going to talk about, I think, in the next unit when we get to acids and bases. No? No? But you don't want ultra pure H2O.
You want them?
It's expensive. Why would you want it?
Like $30 for a bottle.
Something like that. That's right.
Ultra pure is like $30.
Yeah, it's expensive.
What is it to use?
Nothing. But it's used for certain chemical processes where you're trying to eliminate all the dissolved gases that you can get out of it. Yes. I've never had a sip of ultra pure. I don't have a clue. Nobody drinks ultra pure water. It's just not done. Only for certain lab processes.
It's possible, though, right?
Oh, it's possible. Yeah, I guess. I don't see why not. I haven't read the MSDS on it, but I'm assuming it's possible. Next question. Let's move on. 17. All right, we got to get to the biggie here. Okay. All right, 17. So the question is, perform the following lab procedure. 2.00 grams of calcium chloride and 1 gram of aluminum sulfate are dissolved in separate containers with 100 milliliters of water, and they're mixed together. If we had done the lab last week or week before spring break, when I got so sick for those 2 days and we just didn't have time to get to it, we would have done basically the same lab, only it was with different chemicals, not with these 2 chemicals listed here. A white mixture forms. The mixture is allowed to sit undisturbed for 10 minutes, and after sitting, it's observed that the white material has settled to the bottom of the beaker, and a clear liquid remains in the beaker. The clear liquid is decanted, and the white material is filtered, rinsed, dried, and weighed. The amount of product recovered weighs 0.45 grams. What is the solid white product? What is the percent yield? And what is the amount of excess reactant that remains in solution? Okay. So we're starting with 2 different amounts of 2 different chemicals, but the problem is stating that those 2 chemicals are dissolved and then mixed together and a reaction forms. We know a reaction forms because a solid is formed and it falls out as a precipitate, or at least that's the clear indication that's what's happening. All right, so let's start with the balanced equation. Okay, so we can describe that reaction. We've got calcium chloride, and I hope you guys at this point are all clear on how to balance a formula. Why are you laughing? Huh? You can't? Okay. Do you want me to go over it, or you just want to sit there and... Really?
Yeah.
Calcium has what charge? 2 plus. What charge does chlorine have? 1 negative. Do you know why? You understand? Do you know why? Do you understand? Well, where it is in the periodic table is an indication of its behavior. But yes, you could consider that for this purpose, okay? So in order to have a balanced, that is to say, uncharged formula, I've got to have 2 chlorines, which have a 1 negative charge, to balance or neutralize that 2 plus charge of the calcium. Okay? So now we don't have any charge at all. I could put a 0 there, but that's kind of useless. Now, the problem says it's dissolved. So we could go ahead and say it's aqueous, but if you checked on the solubility rules, you'd find that chlorides are almost always soluble, and while there are about 3 exceptions, I think, calcium is not one of the exceptions. So this chloride is going to be aqueous. It's soluble, there's water around, it's got to be aqueous. Alright, and it's going to be mixed with a solution of aluminum sulfate. Okay, now aluminum has what charge? 3 plus. In the periodic table will give you a 3 plus charge. So everything in the first column of the periodic table, oh, I think my screen's frozen here. That's not good. There we go. I don't know if we're going to be able to see much out of it. In the first column of the periodic table, starting with hydrogen, everything in this column generally has a 1 plus charge. In fact, all of them do have a 1 plus charge, except hydrogen can sometimes be negative 1. Column 2 is always 2 plus. This column here, starting with scandium, is going to be always a 3 plus charge, and then we can begins with Zn, the 3 plus. 2 plus. The column beginning with boron is always going to be, and then we get to this starting with carbon, which we don't always know about. It can be sometimes 4 plus, sometimes 4 negative. Then we get to 3 negative, where nitrogen is, that column, in binary compounds anyway. The nitrogen column is always 3 negative. In binary compounds, the oxygen column is always 2 negative. And in binary compounds, the fluorine column, the halogens it's called, is always 1 negative. Okay? So aluminum is going to be 3 plus because it's in this 3 plus column we talked about starting with boron. Then we're combining that with a polymetallic ion called sulfate, and that's just something you have to memorize in this class. You have to know that SO4 is sulfate, and you have to know that that's its name, and you have to know its charge, and its charge is 2 negative. Okay? So to get this compound balanced, we're going to have 2 aluminums and 3 sulfates. So they'll be charge balanced. We'll get a neutral compound. So to show 2 aluminums, I want to put a subscript 2 here. To show 3 sulfates, I want to put a subscript after a parenthesis following that sulfate. And the problem says it's aqueous, but if you check the solubility rules, you'll find out it's aqueous. Okay? Then we've got to figure out what we're going to have on the other side. Well, we're starting with 2 compounds that have 2-part names. And that's a really good clue that we have 2 2-part compounds. Okay? We've got calcium chloride, it's an ionic compound. We've got aluminum sulfate, it's an ionic compound. 2 2-part compounds. The type of reaction we're most likely going to have then is double replacement. And in double replacement, the front part of the first compound joins up with the back part of the second compound. Okay? So we're going to put the calcium with the sulfate. Now, right now I haven't balanced that. I'm just putting them there. And I'm going to put aluminum with the chloride, but I'm not going to balance it yet. I will get to it very shortly. We'll come back and balance those. Okay? Calcium has a 2 plus charge and sulfate has a 2 negative charge, so that one just happens to be balanced already. A 2 plus and a 2 negative neutralizes each other, that's charged. If we look on the solubility rules, or if you memorize your solubility rules, you know that sulfates are almost always soluble except when they're bonded with some exceptions, and that includes calcium. This is an exception to that general rule, so this is our solid we're looking for in the problem. Okay? Now aluminum, remember, is 3 plus. Chlorine is 1 negative. So to balance this, charge balance this, we need to have a 3 here to neutralize the compound. Chloride compounds are almost always soluble, and aluminum doesn't make an exception, or a compound that is an exception to the rule. So this is going to be aqueous. Okay? So we've got our formulas all balanced. Now we're ready to balance the equation. So we're going to list our elements. We've got calcium and chlorine, aluminum and sulfur and oxygen. We're going to make a kind of grid, sort of a mini spreadsheet sort of thing here. And then we're going to count all the elements we have on both sides of the equation. That's what this line is for here, to separate the two sides of the equation. So we've got calcium, we've got one of those. Chlorine, we've got two of those. Aluminum, we've got two of those. Sulfur is inside this parentheses. So everything inside this parentheses is multiplied by what's outside. So this means if I have one sulfur here, it's multiplied times 3, so we've got 3 sulfurs. If I've got 4 oxygens here, it'll be multiplied by what's outside, so that's 12 oxygens. Okay? On the other side of the equation, we've got 1 calcium. We've got 3 chlorines over here. So 3 chlorines. Then we've got 1 aluminum. We've got 1 sulfur. And we've got 4 oxygens. All right. So now we're going to try to get everything balanced using coefficients. And we can only, once the equation is balanced, once the formulas are balanced, you are only allowed to use coefficients to balance the equation. There it is. Looking for a certain type of marker. Couldn't find it. Too bad I don't have my little song queued up here for our new student. All right, so the first unbalanced thing we get to is chlorine. We always save oxygen for last, and if we had hydrogen, we'd save it for next to last. But we don't have hydrogen, so we're really going to start with chlorine here. Chlorine, I've got 2 of those on the left, 3 on the right. The only way to get the same number of chlorines on both sides is I put a coefficient of 3 here and 2 over here. Okay? And that's going to change the number of calciums and chlorines on the left, and it's going to change the number of aluminums and chlorines on the right. And so we need to recount those now. The 3 in front of the calcium means I have 3 calciums, and a 3 in front of the calcium chloride formula means I have 3 times the 2 chlorines that are there, so I've got 6 chlorines on the left. Over on the right side where the aluminum is, I've got 2 aluminums there, and the 2 times the 3 chlorines in the formula means I'm going to have 6 chlorines. Well, why did I mark out calcium? I should have marked out chlorine here. So calcium was fine, but I got to go back and change it anyway now. So if I've got 3 calciums here and only 1 here, then I need a coefficient 3 in front of that species. All right, so that's going to change on this side the number of calciums and the number of sulfurs and the number of oxygens. So we are going to count those now. We've got 3 calciums here. We have 3 times the 1 sulfur, or 3 sulfurs, and 3 times the 4 oxygens, for 12 oxygens, and the equation is balanced. So hope that is the way that I require you to balance equations in here. I need to see all that. Have you done that already? That sort of thing? Okay. You may have balanced equations by inspection. But we use atom inventories, and I give credit for the atom inventory being there on the test or on the homework. Okay? What it does is it forces you to be very organized, and it gives me something to look at if you make a mistake, try to help you figure out what it is you're doing wrong, if you're doing something wrong. Okay? Also, when you get to really, really complex equations, you kind of need something to kind of keep up with everything. Okay? The one thing that I didn't have to do here is if I have a really complex set of things like oxygen can get pretty complex. So I'll write them out here. I do a little math problem out here on the sides to kind of keep up with what I'm doing. All right. So the problem says we're starting with 2 grams of calcium chloride. And we're also starting with 1 gram of aluminum sulfate. So we're going to do 2 separate stoichiometry problems, mass-to-mass stoichiometry problems, starting with these 2 amounts and calculating our way to the product. Now, I hope you may have started with those 2 and only gone to the number of moles and then compared a molar ratio with the equation. That's just not the way I teach it. Both of them work, and in college you might be expected to do that. But the way I teach it is to go all the way to mass all the way from front to back. All right. So we're going to put both of these starting amounts over 1. And the first thing we have to do is to change grams into moles. And what you have to do to do that is you need a conversion unit called a molar mass ratio. And the molar mass ratio has to be calculated, or the molar mass has to be calculated. And from that we extend that a bit to get a molar mass equality statement to build our conversion unit. So we're going to list out, in this case, the 2 elements that are in our calcium chloride compound. We're going to write out their atomic masses. Now, I hope you were given 2 different references. You've got a full set of references which has much more detail in it. But the other reference you have is the type that you're going to use on the test. So this form of the periodic table is the one that you'll use on a test in here. Okay, it's the same one they use in AP chemistry. So this is a prerequisite class for going to AP, and that's why I use that, so you have a better preparation for AP chemistry. And then you've got this stuff on the back. And what was the other reference I gave you guys? I guess I need to get her a copy of it. Oh, that's right. We use the redox for this. And I'll have to get you one of those. Okay? Instead of using a set of solubility rules as a reference, they don't give you a set of solubility rules on the AP exam. You have to memorize solubility rules. But you can infer almost all the solubility rules from a standard reduction potential list. And I said redox. Use this for redox equation. Redox equation, okay? And I'll have to get you one of those. I don't think I have an extra one of those printed. So now we're going to calculate molar mass, and this is the way that I ask you to do it in fact, I require you to do it in my class. Again, it keeps it well organized, keeps you well organized, and it also helps me to find when you make mistakes, what the mistake is. So we're going to list the masses, the atomic masses of calcium. Whoop, that's wrong. 40.08, right? And chlorine is 35.45. We're going to multiply these by the number of those elements we have, or atoms we have in the formula. So since I have only 1 calcium in the formula, I'm going to multiply it times 1. Since I have 2 chlorines, I'm going to multiply that by 2. And then we're going to do the math for that. 40.08. Boy, I'm really I'm having trouble here with just simple writing down numbers. What's the deal? All right, and then 35.45. Well, I can do that one. That's 70.90, isn't it? Okay. And then we're going to add those together. No, that's not right. It's 11. It's 110, isn't it? Okay. So that's your molar mass. All right, but we have to write out from that then in the quality statement. There's no rounding off to be done because you don't have any empty slots over here. So we're going to write 110.98 grams of calcium chloride equals 1 mole of calcium chloride. Okay, there's the equality statement you have to write in order to build a conversion unit. Then we're going to build our conversion unit. And I hope, just for your information, when you get to AP, if you take AP, you won't need to do all this. Okay, but you'll have, by doing this process over and over in here, it'll be in your mind. You'll have the calcified neuron paths all cleared out and everything. You'll be able to do it, real quick in AP. You skip all this and just go straight to that stuff. Okay. So then we're going to put the left side of the equation on the bottom because the units of measurement and the species match the units and species that are in the top of the part of the problem that's before it. 110.98 grams of calcium chloride, and the right side of the equation where we have 1 mole of calcium chloride, that's going to go on the top. And now we go to the molar ratio step. What we've done here is successfully set it up so that we can cancel the units and species of grams of calcium chloride. And we are at the point where we have moles of calcium chloride. We want to go to the other species. The species we're looking for in the problem is the one that is a solid. And we have to kind of do a little bit of mental problem solving here, in that we can see that the problem up here shows that the only solid we have is this calcium sulfate. So that's going to be our product that we're looking for. It's going to be the thing we're looking for in all our stoichiometry problems. Okay? So we want to put the number of moles of calcium chloride from the equation on the bottom. The equation shows we have 3 moles of calcium chloride. That coefficient 3 in front of calcium chloride in the balanced equation could be 3 set of formula units, or if you multiply everything in there by Avogadro's number, we got 3 moles of everything and 1 mole and 3 moles and 2 moles. That's the coefficient in front. So if we're trying to find calcium sulfate, we're also going to have 3 moles of that because that's the coefficient in front of it. And we're going to cancel units of moles in this case and the calcium chloride species. And now we're ready to convert moles of calcium sulfate into grams of calcium sulfate. So we need another molar mass calculation. Yes. And the reason for that is if you make a mistake, I want to be able to help you figure out what the mistake is. Okay, and correct that so that on the next test, you get it right. That's the goal. All right. So sulfur is 32.06, and oxygen is 16. So we got 14, 8, 8. Okay. So this means then that I have 88.14 grams of calcium sulfate in 1 mole of calcium sulfate. Okay?
Did you not count that 4?
What, did I miss something? This 4 what? Oh, I didn't multiply by 4? Man, I'm just having all kinds of trouble today. Thanks for keeping me straight there. And look who it was. Boy, you should pat yourself on the back. Huh? Yeah. You're always saying, boy, I can't do this, and you're concerned about it and everything. And boy, you're the first person to notice. Good for you. Yeah, but you spoke up. Good for you. Here I'm giving you praise, and you're just like, oh well. So, okay, be that way. See if I care. See, I knew you could do it. That's the thing. Yeah, but all the little things add up to the big things, and so you eventually get it all. Yep, here we go. 136.14. I'm glad you noticed that before I built my conversion unit up there. I guess I'm just more tired than I thought I was. Okay. So that's an object lesson. Get a good night's sleep tonight before the test. When you get old like me and you eat spicy food, it keeps you up at night. Don't anybody say anything about me being old now. I can say it, but you can't. Alright, now we're ready to do the math for the stoichiometry problem. Now, the way that I teach you to do this kind of fast is you multiply everything across the top. Of course, really, we got a 3 over 3. We can speed that up, too, because 3 over 3 just cancels out, right? It's like 1 over 1, right? You could do that, right? So it would be 2 times this, hit equals, then divide by that, okay? So 2 times 136.14, enter, because the 3's can cancel here. I'm speeding up your math. If you notice that, you don't have to do that. You'll get the same answer.
Oh, okay.
But if you happen to notice, oh, that's a 3 over 3. If it was a 2 over 2, you could just you cancel out. That make sense? Yeah. Okay. And then we're going to, all right, so I multiply this times this times this. Now I'm going to and I've hit equals. Now I'm going to divide by this. Oh, I failed to hit a number. 272.28 divided by 110.98. Okay. So y'all get 2.43 or 453? 2.45341503 grams of calcium sulfate. All right. On that little heads up kind of thing is I make you write out the entire answer and then underline the insignificant digits and round off on paper. If you don't take AP chemistry but you do something else that requires good solid lab work like you do in here sometimes, it's really important to know what all your insignificant digits are. That's really important to keep up with all that. So this is a good technique to learn now, even though when you're taking the AP test you're going to skip right to the rounded off answer. Okay? But because you're doing it this way over and over again, hopefully in your mind you're going to have it set. Oh, I can do that. I don't need to write it down anymore. I can go right to this rounded off answer. Okay? Now we use an arrow to show a rounding off. Don't use that squiggly equal sign. Okay? The wavy equal sign or whatever. Use an arrow to show that you're rounding off 2.45 grams of calcium sulfate. Okay? Now, that's the first stoichiometry problem. Now we do the second one. All right? Have you already done that one, or do you need to do that now? Find the molar mass of aluminum sulfate. Have you already done that? Everybody's done that? Okay. So what is the molar mass of aluminum sulfate? 342.12? Oh, don't make me do the math.
I got 1.4. Who's 1.4? Two people got that.
Majority rule.
Really? Not in this class. Yes, you got it. There you go. Say what? Well, that's true in American democracy, but it's not true in this class. Okay. So I got 342.15.
If you got 0.14.
But that was using all the numbers before they're unrounded, so that would be different for you guys. That was using the total stuff.
If it's 1 point off on the test, will you count that really wrong?
No, not totally wrong. Okay. No. It would kind of depend on things as to how I would count it off. Okay. So is it 342.15 or 14? Using the numbers you have on this periodic table. 14? Okay. That's grams of aluminum sulfate. And I should have left myself more room here. 1 mole of aluminum sulfate. Okay. Units cancel. That's grams. Cancel. Species cancel. That's aluminum sulfate. Now we need the molar ratio for aluminum sulfate to calcium sulfate. Remember, we're always going to this product right here. Okay? So aluminum sulfate is 1 mole of aluminum sulfate in the balanced equation. And there's 3 moles of calcium sulfate in the balanced equation. So we can cancel moles, units of moles, and cancel units of moles like this. And aluminum sulfate we can cancel. We have moles of calcium sulfate. Now we've got to get to the mass. We've already got the molar mass calculated. So we can just copy this down here. You don't have to do it twice if you've already done it once. You just do it one time. And that's even if in a test, like for instance, you have a molar mass calculation on problem 6, and it also requires the same molar mass calculation on problem 7. You don't have to do it over again. Okay, just say, see problem 6 or something, okay? Does that make sense to everybody? As long as you show it to me, you don't have to do it again. Or tell me where to find it. Oops, sulfate. Alright, so moles go away, calcium sulfate goes away. Now we're ready to do that math. And what kind of answer did you guys get? 1.19? And that's after rounding off? Okay, so do I skip the rounding off step then? And that's grams of calcium sulfate. And we're going to round that off to 3 digits. You're going to look at all the measured or calculated numbers in the problem. These 1s here and this 3 here, those are counted numbers. Okay? Most of the time, whole numbers are going to be counted numbers. So we're looking at all the measured numbers like this, and the calculated numbers like this one and this one, and all those numbers that are measured or calculated when we're doing multiplication division, we choose the one or find the one that has the least digits and write our final answer in that same number of digits. Okay? So this has 3 digits here. That's our smallest of those 3 numbers. 1, 2, 3 is the digits we want. So we're rounding it off to 1.19. 1.19 grams of calcium sulfate. Okay, so what we've done is we've found 2 different masses of calcium sulfate. Got 2.45 and 1.19 grams of calcium sulfate. The smallest of those 2 numbers is the limiting reactant. The smallest of those 2 numbers is the the theoretical yield. The smallest of those 2 numbers is the theoretical yield.
So every mass conversion you on the test, you're going to have to identify what theoretical yield and stuff.
Well, you need to know what the theoretical yield is if you're calculating percent yield.
Wouldn't that make it the limiting reactant?
No. The limiting reactant always has to come from, the theoretical yield always has to come from the limiting reactant. So the way we find the limiting reactant is we just find, well, here's our theoretical yield. We started with aluminum sulfate. That's our limiting reactant. Okay?
So if you know the theoretical yield, that same reactant
the species you started with in the beginning of that problem, when you found the theoretical yield, that species is the limiting reactant. That makes the other reactant the excess reactant. Okay? So you got one that's limiting, the other one has to be excess. Unless you have a stoichiometrically perfect ratio, which doesn't happen very often, but it occasionally does. All right? All right, then, since we know what the theoretical yield is, then now we're prepared to find the percent yield. Percent yield is actual yield over theoretical yield. And the actual yield in the problem was 0.45 grams, I believe, right? 0.45 grams of the solid was collected. The solid we found when we did our balanced equation was the species calcium sulfate. So it's 0.45 grams of calcium sulfate divided by that theoretical yield amount of 1.19 grams of calcium sulfate. And a percent is always, always, always part over whole times 100. And then times 100. So 37.81512,605 is what I have. Now, a little tip. Here's a little tip. Keep up with the units and species the way you're supposed to. All percentages will always cancel all units. Percentage is a unitless answer. Okay? If you haven't set it up right, well, that's one. If you haven't canceled all the units, you've set up something wrong. Okay? Now you don't always cancel the species, but in this case we did. Okay? Sometimes you don't always cancel the species. All right, we want the number of significant digits. This is a multiplication division problem. We have 2 digits here and 3 here. This one doesn't count because it's kind of an absolute number. We want 2 digits in our final answer. I'm draw on everything else. Draw an arrow to show we're rounding off, and we get 38% yield in calcium sulfate, or of calcium sulfate. Either one of those preposition, I think they are, will work. Will be accurate and reasonable. Got it? The last thing, doesn't the problem ask you for the excess reactant remaining? Okay, excess reactant remaining. Okay. The excess reactant remaining, we're going to start with a limiting reactant, and we're going to calculate our way to the other reactant. This one right here. Okay? We're going to be calculating mass to mass from the limiting reactant here to the excess reactant. That will tell us how much excess reactant was used up. We subtract that from the starting amount to find the excess reactant that remains. Okay? So let's do that. Well, we're going to start exactly the same way here. So really, we can copy all of this stuff here and in the second part of the problem and the bottom of this one. I'm sorry. Here up to the bottom of this one. You're right. I was looking at the wrong equation. Okay? Absolutely. You're absolutely right. So 1.00 grams of aluminum sulfate. 3 here. And then 1 mole of aluminum sulfate over 342.14 grams of aluminum sulfate. And then what's on the bottom of this molar ratio, we can keep that part because that's the same we do here anyway. 1 mole of aluminum sulfate. But remember, we're not going to from here to calcium sulfate. That's the product. We want to go to the other reactant. So in this case, we want to have 3 moles of calcium chloride on the top. We want to convert the moles of calcium chloride now to mass. Let me go through. I didn't cancel as I go. And let's see. But we do have that ratio already done right here. And it was used here. So we can actually copy this stage of the problem here because it's what we're going to be using here anyway. We need moles of calcium sulfate on the bottom, mass of calcium sulfate on the top. I'm sorry, calcium chloride. Sorry. We're going to flip this one, calcium chloride. So 1 mole of calcium chloride goes on the bottom here because we've matched the units and species, top and bottom. And then the 110.98 grams of calcium chloride goes on the top. So that we calculate that in the beginning here. This is the equality statement from which we build this conversion unit. You don't have to do it twice if you've done it already once. All right. And now we're ready to do the math for that. So we're going to multiply everything across the top, hit enter, then divide each of the things on the bottom when you divide by separately. We've only got one thing to divide by this time, so that makes it easy. So let's see, make sure I did it right. 3 times 110.98, okay. 0.9731104226. And this is grams of calcium chloride. We're going to underline all the insignificant digits. We're going to ignore the counting numbers. Okay? Those are all the whole numbers here in this problem. This is a measured number. This is a calculated number. This is a calculated number here of those 3 numbers that really matter to us in rounding for multiplication and division. This one has the least digits, so that's how many digits we want in our final answer. Leading zeros are not significant. 1, 2, 3. Underline everything else. Draw an arrow to show we're rounding off. 0.973 grams of calcium chloride. Okay? This is the amount of excess reactant used up in the reaction. Okay?
When you used up, I thought it was just not used if it's extra.
Yeah, that was the amount remaining, isn't it?
Now, the amount remaining will be when we subtract this from the amount we started with.
So that's how much
Oh,
is
okay, yeah,
used.
yeah.
You got that?
That's what I did.
Okay. All right, so here's the deal. Limiting reactants run out first, right? Okay? When it runs out, the reaction stops. When it stops, then there's going to be some of this excess reactant left over. But not all of it's left over. Some of it was used in the reaction. This is the amount that was used in the reaction.
But that's what CaCl.
Right. That's the excess reactant. This is the limiting reactant. This is the excess reactant. When this stuff right here runs out, there's going to be some of this left over, but not all of it. Some of it had to be used up to react with this, with the limiting reactant.
So that's how much reactant you have.
That's how much you got it, how much reacted with it. So to find out how much is that excess, we just subtract. We started with 1 gram, right? 1.00 grams of aluminum sulfate. And we're just going to subtract, 0.973 grams of aluminum sulfate. Okay? Zero 0.027 grams of aluminum sulfate. Now here's another little tip.
Why are you subtracting that aluminum sulfate and calcium?
Duh. Forget what I just said. Alright, so we're going to start with, what was it, 2 grams?
Yeah, 2 grams of
2 grams. Okay, 2.00 grams of calcium. I told you I'm tired. I'm sorry. Did you do that?
Yeah.
Okay, well, we'll clear that up right now. We were wrong. Alright. So let's see. Now we're going to have, make sure, because I'm so tired, I want to make sure. .027. Okay. Now this is addition and subtraction, so we know that we have an empty slot above this 3, and that 7 is going to be insignificant. Grams of calcium chloride. And we're going to round it off then to 1.03 grams of calcium chloride. That's how much is left over when the reaction finishes its course. Now, why is that important? Well, let's say you're trying to get rid of all the calcium chloride. Maybe calcium chloride is the stuff that's dangerous and you want to get rid of it. You want to neutralize all of it. This is how you figure out how much to start with, to figure out what the stoichiometric amount of some more aluminum sulfate is to get rid of it. Yes. Yes. Yes.
How do you set up the equation you just did up there?
This one?
Yeah.
Once you find your limiting reactant, everything starts with that.
Okay. And then
Okay?
you go.
From limiting reactant to excess reactant.
And that finds what was.
Used up in the reaction. The amount that was used up in the reaction. Then you subtract from the starting amount to find the excess, the amount left over. The excess remaining, let's put it that way. That's a better way to say that.
And then if you want to do the percent composition, is that what it is?
Well, that was on the previous page. We didn't do that yet? Man, I am just out of it. All right, percent yield. Wait, we didn't do percent yield either, did we?
But percent yield is not even 16. You didn't ask it for it.
I did?
Yeah, that's what I meant.
Okay, 16% composition. Percent yield we haven't done yet, right?
Yeah, we have.
Did I do it?
38%.
Oh, 38%. All right, percent composition then is a different thing. Do you want me to do that too?
I mean, can we just do it for this one?
Sure. For which species you want me to do it for?
Oh, okay. You don't have to do it for all of them?
No, you only have to do it for one compound.
When you ask for it?
Mm-hmm.
Okay. I guess just do 16 then.
Do 16 then. Okay. I can do it. Let's see, 16. It asks for the percent composition of aluminum oxide, Al2O3. All right. To try and keep things consistent and make as much as possible things set things up in the same way every time as much as we can, I ask you to do percent composition start with the way we do molar mass calculation. So we're going to calculate the molar mass of aluminum oxide. So aluminum is 26.98. Oxygen is 16.00. We have 2 of these, 3 of these. Whoa, 26.98 times 2, 53.96, and then 16 times 3 is 48. And this is something you have to be careful about. I mentioned this, I think Monday. If you just put this in the calculator, you're going to get just 48. But you need to know, multiplying this number times 3 is the same thing as adding 16 to itself 3 times. And if I'm adding 16 to itself 3 times, I'm going to get 48.00. Okay? You need to know that there's 2 more zeros on this. All right? Because this answer is not going to have 2 significant digits. It's going to have 4. Yeah. Yeah, that's fine. I mean, you get pretty much the same answer, but on the test tomorrow, you'll be using this one anyway. All right? And it's a practice test we're working on. So, anyway, let's see. 101.96, and we said this is grams of aluminum oxide equals 1 mole of aluminum oxide. All right, now, in that 1 mole of aluminum oxide, the mass of just aluminum is this number right here. In that 1 mole of aluminum oxide, the mass of just the aluminum is that right there. So this is then grams of aluminum in 1 mole of aluminum oxide. And in that 1 mole of aluminum oxide, the mass of just the oxygen is this number right here. This is grams of oxygen in 1 mole of aluminum oxide. So since we have the same amount of aluminum oxide, we can use this molar mass calculation then to calculate the percent composition. Okay? So to find the percent of aluminum in 1 mole of aluminum, we're going to take 53.96 grams of aluminum and divide it by 101.96 grams of aluminum oxide. Okay, and remember that percentages are always times 100. It's always part over whole, and that's the part that's in 1 mole. That's the whole in 1 mole. The whole in 1 mole. All right, 53.96 divided by 101.96, and then times 100. And we get 52.92271479 round it off to 4 digits, and we end up with 52.92% aluminum in aluminum oxide. And we got to do the same thing now with the oxygen. 48.00 grams of oxygen. Oh, I want to point this out too. Percentages are always unitless, but here's the case where we don't cancel out the species. Okay? And so it's aluminum in aluminum oxide, and that's what I wrote over here. Does that make sense? I could have written it Al/Al2O3. That means the same thing. Okay? Yep. As long as it's thorough and reasonable, it's fine. I'm going to accept it. And if I don't accept it, you can always call me on it. And not in class. You know, you come up there and ask me, can I get credit for this? Because I think this is right. You know, I'll talk to you about it. Got it? I know you call me out in class all the time, but you shouldn't. And there's a certain point where, you know, you call me out the wrong way at the wrong time, why, you know, some bad things happen. Yeah, you always kind of get right up to the line and stop somehow. What? Why? You liked him? Yeah, he's a pastor. He's going to school. Somebody told me he used to be a police officer. I didn't know that. Oh, is that what it is? Well, I'm friends with the sheriff. Who shot the sheriff? 47 point. Really? You probably need to have the sheriff's call on you. All right. Oh, by the way, anybody listening to this recording, that's a joke. Okay. Now, to check your work, you add these two percentages together. Okay? If you've done everything right, these two percentages should add up to very close to 100. If not exactly 100.
I think this is exactly 100.
You're right. So if you add them together, you get 100% total, and that's your check. Okay? You don't. You're not required to add them together.
Is it supposed to equal 100?
That's the idea. That's how you check it. Okay?
What if it's a little bit off?
Yeah. That's what we said before, that sometimes you'll get like 100.01, or you'll get 99.99%. That's close. That's because we're rounding off as we go, and that continual rounding off propagates an error. Okay? Actually, even if we didn't do that, occasionally we get off to like a thousandth or something like that. All right? Any other questions about all this? Are you guys thoroughly prepared for tomorrow's test now?
What is
I like that.
equal to?
A mole. Well, Avogadro's number of anything is equal to a mole of that thing. Yep. You could.
So I can have a mole with a mole?
Absolutely. If you got to get enough of those little mole animals, I don't know if you could have that many mole animals, because they probably cover the earth up to the moon or something. That's a lot of moles. Are those little skin things, they call a mole? I mean, you wouldn't even be able to see the person anymore. That'd be gross, wouldn't it?
So it's a big number.
It is a really big number. It's 6.02 and 21 zeros.
So that means that much of it makes it a mole?
Yeah.
What is a mole?
Ha! Boy, that's kind of a big question. Let me see if I can answer this simply.
Is it just like a liter?
No. A mole is the official system of international units way of determining the amount of stuff or the amount of a substance.
Well, couldn't you just say 5.00 times 2 would be a mole of that thing? Couldn't Avogadro just say that? Why is that significant?
Well, the mole actually goes back a long way. At one time, they used oxygen to define what the mole is. But now they use carbon-12. It's kind of our basic starting place to decide what the mole is. The reason we have this thing called the mole is because it makes all this math easier. It simplifies all the math. So it's just, without the mole, you'd be using Avogadro's number for all these conversions. You really want to do that? I wouldn't either. That's a huge number.
Hey, did you touch it?
What is it?
My. I only didn't have two little children.
Oh yeah, here's that.
Well, why did you get that when I called for it? I looked on her desk and I didn't see it.
No, you looked at it and you didn't want to look for her stuff because it would cover it and then you walked by it.
Can you vouch for her that she had that video of mine?
It's only been like 2 years.
You barely can tell
How far did you travel?
Well, no, he knew me because he beat me up all the time. Like, huh?
I'll do it.
It's mean. Like, he seriously kicked me.
He's the devil.
That's so obvious. But he's so cute.
Alrighty. So, object lesson in my behavior today. Get a good night's rest.
I actually got here pretty school today.
Huh? You slept in school today?